Good evening students. Today's topic is mechanism of current flow in a conductor and the concept of drift velocity. As already I have told you, a current flows through a conductor whenever across the conductor, if there is a potential difference developed, a potential difference is maintained, then the current flows through that conductor. That's a simple mechanism. So microscopically, let us understand what will happen. Before that, let me explain you the structure of a conductor. Suppose you take a copper wire. How the atoms in a copper wire are arranged, if you do not know that, then the microscopic reason will be very difficult to understand. So already I have discussed the structure of normal bulk solid or bulk metal. Like suppose if you take a copper wire with you, so that in that copper wire you will be having your copper atoms. All the copper atoms, they are arranged in a regular fashion, in a regular arrangement, and that arrangement is repeated over the entire bulk material. Bulk material means suppose you took a copper piece of like this, then that is called your bulk material, means where it's a collection of large number of the particular atom of the particular element. That's called a bulk material. So basically in a copper any kind of conducting material or conductor, if you take, so the atomic arrangement are regular. They are called crystalline arrangement. Got? So in a crystal, all the atoms, they are located at their places. And for a good conductor, typical conductor, they have large number of free electrons, like of the order of like 10 to the power 28 number, 10 to the power 28 number per meter cube. If the volume of the conductor will be 1 meter cube, if you take, then for per 1 meter cube you will find 10 to the power 28 number of your free electrons. And it's a variable one, but the order will be like that. So if you see, the number is very huge. Suppose if you take a conductor and place it in your lab on a table, then what is happening inside? There are large number of free electrons. The free electrons gather thermal energy from outside, and all the free electrons, see, it is a statistical process. We cannot see the electron directly. So it's a process. So it's a statistical process where it can only guesswork, and like we can see like the thermal motion of the gas particles, like that. So electrons, when they acquire the thermal energy from outside, they are in a state of random motions. Like if you see the path of an electron inside a conductor, you will see they are random motions like this. And you see here, up from here to here, the electron is moving in a straight line with a speed of the order of 10 to the power 5 meter per second. That you can calculate by using your your speed distribution formula. That means RMS speed 3 RT by M formula. If you apply for the electron, then you can find that the order of magnitude will be up to you 10 to the power 5 meter per second. This is called a thermal velocity. So suppose in a conductor there are, let's say, 100 number of electrons. All the electrons, they are in a state of random motion. So let us, if you consider for a particular electron, this is the path in which the electron will move. Actually it is a random one. So why this thing is happening? See, because there is no one to control the motion of the electrons, and also the lattice, the regular arrangement of the atoms, that is called your lattice, and the lattice also absorbs the energy, and they are in a state of vibration, and their vibration disturbs the path of the electron. And also not only one electron is moving, because per cubic meter, 10 to the power 28 number of electrons are present. So because of the presence of large electrons, there will be collisions in between the electrons and also between the electron and the wall of the crystal lattice. Clear? Or with the ions we can say. So because of that reason, the path of the electron continuously changing. Clear? So if we try to find out the average velocity of an electron, suppose if you see like let's say there are 1, 2, 3 up to n number of free electrons present inside the material, and because of the thermal motion, if one will try to find out their speed, you will find the speed will be of the order of 10 to the power 5 meter per second. It is a very huge speed. Clear? So suppose if you see the first electron speed is u1, and second electron speed is u2, and the third electron speed is u3, and up to the nth electron speed is un. Then if you can average out the speed, you can find the average speed for an electron, or average you can say that a velocity if your direction is considered. So the average velocity because of the thermal motion, if you count, that is u1 plus u2 up to un, let us take to be your capital N, this divided by n, because this is your average velocity, you average, this is because of your thermal motion, then it would be 0, because the motion is random. So why it is 0? You see, if you see at a particular cross section of a conductor, you will find if 10 number of electrons is moving towards right, 10 number of electrons will moving towards left. So the net flow of charge or velocity for every positive value of the velocity, you will get a negative value. So the average thermal velocity becomes 0. But so it means, though the concept is here, though there is a motion of the charges, though the electrons, because when they acquire thermal energy and they are bound inside a conductor and they are moving, their average thermal velocity is 0. Because of that reason, there is no net current flowing through the conductor in the normal situation. The normal situation means if you take a conductor and place it on the table, you will find, if you microscopically see, then you will find the electrons are moving inside, but there is no net flow of current because their average thermal velocity is leading to 0. Got? Now, if a conductor is there, suppose you have a conductor here and you are providing an electric field. So what the electric field extra doing here? Suppose this is the negative terminal, this is the positive one, this is your conductor. Because of this battery's potential, an electric field is set inside the conductor in this direction. Try to understand. Here it is a higher potential, this side is connected to the lower potential. So here one field is set up from higher potential to lower potential. So let us consider the conductor now. See, no one has control over this thermal velocity. That depends on the temperature. Clear? So when an electric field is set, what the electric field is doing? Because we know electron, they have charges, and an electric field, they exert a force on the charge, and the formula is F is equal to QE. Clear? Since the electron's charge, we know it is a negative charge, so we can say F is equal to minus E of E, because the charge on an electron is E minus E, so E multiplied with the electric field. So force is equal to minus of E into E. It means, actually it is a vector equation. It means the electron experience a force opposite to the direction of the electric field, and the force is given by this much, F is equal to minus of EE. And this force because of the field can accelerate the electron, and we can write which is m into a. It means here m is the mass of the electron, a is the acceleration of the electron. here, the force experience is given by m into a. Here a is the acceleration of the electron and m is the mass of the electron. So if you compare these two, you can get the acceleration will be equal to, that is, minus E by m into E. So which means the electron get accelerated opposite to that of the electric field. Try to understand. Got? So all the electrons, because there are n number of electrons, that n number of electrons get accelerated inside that electric field. Clear? And that is opposite to the electric field. And one interesting thing you see here, acceleration, if the electric field is a constant electric field or a uniform electric field, E by m for an electron, it is a fixed value, and electric field, if it is uniform, then acceleration is a constant one. So it means what? Apart from the thermal velocity, whenever you are applying an electric field across a conductor, that conductor's free electron, whatever present inside it, they experience a force which causes a constant or uniform acceleration in them. It means what? Their speed will gradually increase. Clear? Their speed will gradually increase. But it's not like that. The speed increases to an infinite value. Why so? Because once the electron gains some kinetic energy, so see, from here to here, if it is the electron is moving and it is again colliding with the other electrons and with the wall of the lattice, wall of the crystal, or with the ions, we can say. So when the electron gains the velocity from a particular point, after a certain period of time, it is colliding with the wall. It means the energy, whatever it gains, it releases there. Got? So it means this acceleration lasts for a short period of time, and that time is called relaxation time. Got? Suppose our electron starts its motion from here, and because of that acceleration and reaches here and collide with another electron or with the wall of the lattice, then in between this time the electron is free to move, and it means it is free and it is relaxed. So the time interval between these 2 points is called relaxation time. Or that we can define, the relaxation time is the time gap between two successive collisions of an electron. Clear? So see, my point is, electron acquire a velocity apart from the thermal velocity, because this thermal velocity is because of the outside energy. Yes? So now we can say, if suppose these are the number of electrons 1, 2, 3, 4, 5, 6. Suppose you are noticing one electron particularly. So the particular velocity, the electron's velocity at a particular instant of time is u1, and its velocity will gradually increase because of this acceleration. Now, since the acceleration is constant, so we can apply the equation of motion here. Means v1 is what? Suppose for the first electron, the relaxation time is t1. Means the electron at a particular moment, the first electron speed is u1. That electron gets accelerated and the speed becomes v1. Between the u1 and v1 speed, the time elapsed by the electron is t1. That is called relaxation time. So we can say v is equal to, the formula v is equal to u plus at, as that equation is applicable here because the acceleration is constant. So v1 is equal to a into, means we can say v1 is equal to u1 plus a into t1. Since acceleration for all the electrons is constant, so here I am taking it to be a. Here u1 is the initial speed of the first electron and t1 is the relaxation time. Means the time gap in between which the velocity changes from u1 to v1. Similarly, we can take it for the second electron, which is u2 plus a into t2. So you can take the vector equation. Clear? So this will be the value equation here. Similarly, we can take the value for the nth electron. It will be un plus a to tn. So the velocities of corresponding electrons, and t1, t2, tn, they are the relaxation time for the corresponding electrons. Now see here, if you can find the average value of the velocity for a particular electron after a certain time, then the average value is given by V average is equal to V1 plus V2 plus Vn divided by the number of electron present. So you can take it to be capital N. Already I have taken capital N, that's why I take capital N here. Now you see, you can put the values here. V1 is equal to U1 plus A T1 plus V2, which is U2 plus A T2 plus up to your Vn is how much? That is Un plus A T n divided by n. So which implies actually this average velocity with which the electron travel inside a conductor, yes, the average velocity with which the electron moves inside a conductor is called your drift velocity, and this term will be denoted as Vd, which you can write here, which is, let us separate, see here it is U1, U2 up to Un, that let us separate it, U1 plus U2 up to Un, here divided by n. I have just separated the term, plus here it is AT1, it is AT2, here it is ATn. Now you can take the A common here, A term taken common, which is T1 plus T2 up to Tn divided by n, because n is divided in both the terms. So which implies your Vd is given by, all of you just see, this term is the initial average thermal velocity, which is your 0. Already mentioned. Why it is 0? Because the motion is random, so their average value will be 0. And I'll be getting Vd is equal to, which implies Vd is equal to A vector. See, I can define this entire term, it is the average relaxation time for an electron. So here, this is the average relaxation time, because it is added for the time, the relaxation time is added for all the electrons and divided by n. So it is your average relaxation time, which is denoted by tau. So your tau refers to your this is called relaxation time or average relaxation time, which implies, now if you can see here, means we can write your Vd means drift velocity is given by A tau, and we know the value of A is what? Minus E by m into tau. So this is the required formula for the drift velocity of an electron inside a conductor. Means this is the formula for your drift velocity. Clear? So actually this is the velocity with which a charge is flowing inside a conductor. But this is not the velocity with which the charge is moving. It is the thermal velocity. It is because of the thermal motion, which is not constituting the electric current. So this velocity is responsible for the current flow inside a conductor. Now you can change this equation, like suppose across that conductor, suppose you have taken that conductor whose length is L. Across that, through a battery, you are maintaining a potential difference of V. So in that case, we can have the mod of E can be V by L. That formula is equal to dV by dr. So the equation will become, you can write the scalar value here. So Vt will become simply E tau by m, or which is equal to, instead of E we can write E, instead of electric field, that mod will be V by L into tau divided by m, and your final answer would be Vt is equal to E V tau by m into L. Got? So this is the formula for the drift velocity in terms of your potential difference and relaxation time, average relaxation time. This is mass of an electron, charge on an electron and length of the conductor here. So Vd depends on these following factors. Remember, V depends upon the source, L depends on the geometry, tau depends on the nature of the material. So you can analyze in that sense. E by m is constant for all the material, but V depends on the source used here, potential difference maintained, and L depends on the geometry, means length of the conductor, and this relaxation time, it depends on the nature of this material, what kind of material you are taking. So this is the relaxation time, means as Vd depends on the relaxation time, so that relaxation time of value of the relaxation time for a particular conductor, Vd will be decided. And if you take for example, and if you want to calculate Vd, if the order of Vd will be very less, it is of this a few millimeter, the order of magnitude of Vd will be few millimeter per second. The drift velocity order of magnitude will be few millimeter per second, means the electrons get drifted inside a conductor whose value is to few millimeter per second. So students, this can be your derivation. So question will be like this: derive the formula of drift velocity in terms of electric field and in terms of relaxation, air time and potential difference. Clear? Thank you.